talking about electricity sources, where electricity comes from in different parts of the country, and just a few other things I wanted to mention about, and then we'll start in petroleum. So, when we talk about electrical power sources, it's a distinction that is really important is whether they're dispatchable or intermittent. So dispatchable sources are things that you can call up and say, I need this much power, and somebody can respond to an increase in demand or not. Intermittent sources are sources that, like wind and solar, where the weather controls whether or not you're going to be able to generate power. You can't call up a wind farm and say we need more power. You can't make the wind blow harder. You can't do that with a natural gas plant or a biomass plant or coal plant. And so, as you can imagine, it's well, almost, it's not quite true, but it's almost true that if you build a wind farm or a solar farm, for example, and you're relying on that to provide electrical power for your customers, you have to, in addition to that, you also have to build something that's dispatchable so that if the wind's not blowing, you have a backup source of power to generate that power. And so, to some extent, now if you build, so we have grids, so the wind, even if the wind's not blowing here, it may be blowing someplace else, and so that's not entirely true. But the first order, the real cost of a lot of these intermittent systems is the wind farm and the solar farm, plus a natural gas plant or something else that will operate when those aren't operating. And so that makes them inherently more expensive than just building a natural gas plant by themselves. But if you tie the wind, if we do have a reasonably good grid, if we have a much better grid, then you can start to rely on the wind, even though you could say we can't rely on the wind blowing here at any given time. We can rely on the wind blowing somewhere during this time when it averages out, so that you can start to build a whole grid on wind power. But because of those things, energy storage is a huge, huge issue. So thinking about those things, there are two other important concepts that are important for all. Actually, this is for plant and equipment in general. So the first is the availability, which is a fraction of the time the plant is capable of operating. So this, even if you're just producing chemicals in the petrochemical industry, availability is a big issue. So plants have to occasionally be maintained, brought offline for maintenance. They aren't entirely reliable, so things break unexpectedly, and that brings them offline. So people track the availability, saying these plants were available X percent of the time. So a typical industrial average is 70% of the time for a steady state, 70 to 80% for a steady state type of thing. Power industry, however, has some of the highest availability of any processing plants anyway. So the availability of most dispatchable power facilities is over 90%, sometimes over 95%. So 90 to 95% of the time they are available to produce power if you need power. So availability factors into the second important concept, which is the capacity factor. So just because you're available to produce something doesn't mean that you're actually producing it. And a major factor in the cost of anything is how much of the time your equipment is staying busy. And so the capacity factor is the nominal nameplate, it's the amount of product that you actually produce divided by the amount you can produce if your plant were operating all the time. So a capacity factor of 50% means you're producing half as much material as you would be able to produce if the plant were operating all the time. Capacity factors for dispatchable power systems are also industry-leading numbers typically, so they're typically in the 80 to 90% range. But for intermittent systems, for wind, for example, they're 30, at best 40, sometimes 20%. For solar, much less than that typically. So that is, the windmills spend most of their time idle and only generate power. Now, why is that so important? So we will, in this class, we will go through, you will learn to do these calculations. But when you calculate the cost of anything, whatever you're producing anywhere in the chemical industry, there's a number that figures prominently called the levelized cost. So what goes into the cost of anything are one-time expenditures, like the cost of building the facility to be able to produce it, those kind of capital expenditures, and operating expenditures. So as you operate it, there are also costs associated with operating it. So how do you take all these very different kinds of costs and factor them into production? And the process of doing that we call levelizing the cost. So you say, if I'm not going to operate this piece of equipment for 30 years, then I can amortize that capital cost over 30 years, and the operating costs that I have, the fuel costs in the case of power, they come in proportion to the amount of product I produce, and the total cost of my product is some combination of the one-time cost, capital cost mainly, and the operating cost. So in power production, the fraction of the cost of electrical power that you produce depends very strongly on the technology, the fraction that's associated with the capital cost. So for nuclear power, for example, about 90% of the cost of nuclear power from a nuclear power plant is the capital cost associated with building the power plant. So operating the power plant, so again, this is not exactly true, but the first order, the cost of nuclear power is the same whether you're producing power or not. So once you've built the plant, you're stuck with those capital costs. You're still going to have to pay the interest on loans. You still have to maintain the plant. So all of those fixed costs are stuck in it. And if you're generating the power, it only changes your cost by about 10%. So the cost is the same whether you're generating power or not, or almost the same whether you're generating power or not. At the other extreme, natural gas plants are only about 25%. About 25% of the cost of a natural gas plant is associated with the capital cost. And for solar and wind plants, over 90% of the cost is the capital cost. So once you've built the windmills, they're relatively inexpensive to maintain and to operate. So almost all of the cost, and the same is true of the solar cells, so almost all of the cost is associated with that initial cost. So the capacity factor figures prominently in there. So if you build something, say a nuclear power plant, but you only operate the nuclear power plant half of the time, you've doubled the cost of the electricity coming out of the nuclear power plant because you're only producing half as much product and the capital cost is the same. By contrast, if you build a natural gas plant and you only operate it half of the time, the cost of the electricity from that natural gas plant is mostly the cost of the fuel that you're burning. So not operating the natural gas plant saves you money. Not operating the nuclear power plant doesn't save you anything. It costs the same amount to not operate it as it costs to operate it. So those kinds of factors, the capacity factor figures prominently into those kinds of discussions. And those are concepts that are important to think about when you think about how we use power. So specifically for electrical power, there's also, so those concepts of capacity factor and levelized costs and availability are uniform across the entire processing industry, so not just power production. But for power production, there's another couple of really important things. And one of them is that some power plants really want to be operated all the time at a constant load. Nuclear, again, is a good example of that. Nuclear power plants, coal-fired power plants are examples of things that really don't like to change load. So they don't like to change load because they're very high-pressure systems, and in those so this is fascinating to me, is that inside of this complex system, there are these high-pressure pipes that have high-pressure steam in them that get welded to headers. They're called that steam, and prepared to go into the turbine. And those are at 200 and some bar pressure, so some of the highest pressure things that we normally operate with. Anything that's higher pressure than that, there are very few plants that operate at pressures above 200 bar. Power plants operate routinely around 250 bar. So, that is the steam in the power plant, is 250 bar. So 250 bar at 600 degrees is really difficult to contain, and the vessels that they contain them with are very thick metal vessels that are built to contain that kind of pressure and that kind of temperature. But when you change the load of the power plant, the temperatures shift all the way through the power plant, and that means that the temperatures of the steam tubes shift, not by a lot. You're still making steam, but they shift a little bit. And specifically, when you weld the pipes that carry the steam into the headers, that weld, interestingly enough, is usually the thing that controls how rapidly you can change the load of the power plant. Because if you change it too fast, the thermal stresses that get set up around that weld are large enough that the weld starts to crack over time, and you have a catastrophic failure of the power plant. So, you know, of all the things that go into a power plant, the weld of the steam tubes to the headers is the thing that controls how fast you can do it. And in any case, you can, you know, typically these power plants want to change a few percent load per hour. So 3% of the load per hour is about as fast as they want, as they can handle to use the load. And the demand for power, electrical power, and the supplies are change much more rapidly than that. So a wind farm, for example, might go from idle to nearly full production in 15 minutes as a front comes through and all the windmills start spinning up. And so the power plant, the nuclear power plant, the coal-fired power plant just can't manage it. You can't dial them down as fast as the windmills come up. So, and same with the sun is even more dramatic. So the cloud goes in front of the sun, your solar plant goes to 0 in a minute, maybe 2 minutes. And so those are really rapidly changing loads. So baseline load plants want to produce the same amount of power independent of demand. Nuclear, coal, and we'll talk about what this means, natural gas combined cycle plants, and essentially any other plant that has high pressure steam and the headers and those kinds of things. All of those kinds of plants don't like to change load. Cycling these kinds of plants is really damaging to them. Load following, or sometimes called peaking plants, adjust to the output to match demand. So these are simple cycle turbines and also natural gas, but not combined cycle. And reciprocating engines are the most common in the load following plants. So it's pretty common that you'll have, in fact, down in Mona, if you drive south of here, some of you, if you've been headed down to the national parks, if you look off to the west, to the right, as you're driving south with the freeway, there's a big natural gas plant down there that's one of those load following plants that we use around here to follow the demand and load. So that distinction is also pretty important. Let's see, we talked about levelized cost already. The other thing that I didn't talk about is the avoided cost. So you would think that the simple-minded way of deciding what power plant you want to operate would be to say, well, which one costs me the most money? I'm going to turn that one off, right? When you have more capacity than you have demand, you might think, well, I'm going to turn off the one that costs the most money. But frequently, the one that costs the most money is going to be the nuclear power plant right now, if you have one in your system. But if you turn off the nuclear power plant, you don't save anything, right? It doesn't save you any money at all. And furthermore, you damage them. So cycling it on and off is really damaging to the plant. So even though nuclear power plants in many jurisdictions have some of the highest average costs of electrical power production, that's not true uniformly, but many of them do. They operate all the time because you don't save anything by turning them off. The ones that get turned off are the natural gas plants because you actually save money by turning them off. You're not consuming the fuel, and that fuel is a big cost, a big fraction of the total cost of electricity. But the avoided cost is a real way to say which one I want to operate, is to compare the levelized cost with the avoided cost. And that is to say, if instead of, especially if you're trying to build new capacity, instead of asking the question, which one of these would be the cheapest to generate electricity, which one would have the lowest levelized cost, the real question you want to ask yourself is, where can I get the biggest gap between the avoided cost and the levelized cost? So the avoided cost is how much it would cost you to generate an additional increment of electricity if you didn't add any new capacity. If all you had is what you have right now, and somehow you have to ramp that up, then how much is that costing? So let me give you a specific example of how this can be kind of tricky. So in Utah, for example, we have a mixture of coal and natural gas, mainly coal and natural gas, and a tiny bit of wind and a little bit of solar. So many of the natural gas plants don't operate very frequently. So the capacity factors for many of them are probably less than 20%. So even though natural gas has the lowest levelized cost, if it were operating all of the time, because it's only operating 20% of the time, the cost of electricity from these facilities that almost never operate is very, very high. And so if I'm trying to decide whether I want to build a new nuclear plant, that's a discussion going on in Utah right now. Do we want to build a nuclear power plant? What I want to do is say, if I build this nuclear power plant, this is what I think the cost of electricity will be from the levelized cost of electricity will be from that nuclear power plant. If I don't build a nuclear power plant, then I have to generate that electricity from some other means. Well, one of the choices is to continue to generate electricity from these intermittent sources, and they're very, very expensive. So if the nuclear power plant can replace those intermittent sources, it makes a lot of sense. But because those intermittent sources, that is, because those intermittent sources are mostly load-following plants, not base-load plants, and the nuclear system can really only displace base-load power, then instead of asking whether I need to, so in the case of a nuclear plant, what it's going to displace is a coal plant, for example, or a combined cycle natural gas plant. It's not going to displace these very expensive, rarely used cycling plants that are only peaking plants. And so I have to compare the cost of the nuclear plant to what it would displace if it's going to be doing it. That's called the avoided cost. On the other hand, if I have something that's intermittent, something that can do load following, and it can do it more effectively than these other load following plants, those are almost always the most expensive sources of electricity, because they don't produce very much electricity, but they're the ones that produce the electricity that follows the demand, so that we always have electricity available for us. So, with all of that in mind, these are levelized costs of conventional power generation and alternatives for power generation, and this is a comparison that you can use to see how much different things cost. So you can see that natural gas is the lowest. Well, actually, we'll talk about this in this class. Energy efficiency is the lowest cost. So if I can do something to not consume electricity that's effectively the same as generating more electricity, if I decrease the consumption somewhere, that's effectively the same as increasing the generating. We have way more cheap opportunities to do that than anything else, and there's actually a significant amount of electricity that can be generated by decreasing the amount of electricity we consume. That's the cheapest thing to do. Right now, the next cheapest is typically natural gas, and then you see a very broad range here for coal. This is conventional coal without, well, this end would be coal with carbon capture, actually maybe even higher than that, getting rid of CO2. This is conventional coal. And then you come up into these things and look at the solar costs. So rooftop solar is really expensive, but there's also a large subsidy for rooftop solar, and if you install this, this is what it actually costs to generate the electricity, but the government, i.e. all of us, help pay some of that cost, and so the actual cost to the consumer is actually fairly significantly lower. Almost all of these alternative energies are subsidized to some extent, but you can see how they fall out. It used to be, interestingly enough, that the solar thermal that you see is pretty expensive here. It used to be the cheapest form of solar power. If you drive past Las Vegas into California, and you look off again to the west of the freeway, you can see standing out in the desert this big tall tower that Google, among others, have invested in. And at the time they built that, which was only about 7 years ago, solar thermal was the cheapest form of solar power that you could generate. And so they invested a lot of money in that plant. So it's a big reflecting, so it's one of these solar tower plants where they reflect solar energy to the top of this tower, and at the top of the tower they melt salt, and that hot molten salt goes down and eventually generates steam and generates electricity. So that plant turns out to be producing about 1/4 as much as they thought it was going to produce in terms of the electrical power coming out of it. And in that same time, the cost of photovoltaic power, so solar cells, so as opposed to solar thermal, went from clear up here to clear down here. So it's now way cheaper to build photovoltaics and a lot less hassle than it is to build solar thermal. So Google thinks that the United States government should bail them out of that investment in that power plant, because Google is such a struggling company economically, and the other investors that are involved in that, they're petition. They have about $250 million invested, which is about a fourth of the cost of that plant in that plant. And so here, let's see. So in general, these come offshore here. And if you look at the range of estimates of power costs, these are the levelized costs for lots of different things. And you can see some of these have incredibly high ranges, depending upon how they get. This natural gas combustion turbine runs all the time. It's one of the cheapest forms of power you can generate. But if you're only operating it as a peaking plant, it can get extremely expensive because you don't use it that often. And so the costs from those peaking plants can be really high. So we'll look at electrical power next. So those are the things that's what I was hoping to get through yesterday, and we didn't quite get all the way through it. So today we start talking about petroleum. Any questions before we start the petroleum stuff? So that gives you kind of a lot of broad concepts. So I'll come back to this again, and we're going to kind of go through these in this order, starting with petroleum. So we use more energy in the form of petroleum than anything else in the United States, and that's also true globally. Petroleum is the largest single source of primary energy that we use. Not necessarily the largest source of CO2 because it produces less CO2 per unit energy than coal, for example, but it is the largest single source of primary energy.
So I had a tough time finding the exact or relative number for fossil fuels consumption worldwide and for the homeless. So I was curious what that number was.
So we'll look at that worldwide. Actually, we had that in our presentation earlier. I had both the global and the U.S. statistics in the notes from yesterday.
I saw that 80% for U.S.
For total fossil. Oh, yeah. Yeah. So for the world, it's also turns out that the U.S. has dropped from about 85 to about 81% in the last 4 or 5 years, mostly because of the decline in coal. But the world is still about 85% as well. So the U.S. and the world, there are local regions of the world where combustion is less than, fossil fuel is less than 85%. France, for example, has a lot of nuclear power, and so they're quite a bit less than that. Iceland has a lot of geothermal power, so they're less than that. But if you average things over the whole world, it's about 80 to 85% worldwide fossil fuels. All right, so let's see. So we use a lot of petroleum, and I suspect in your homework you were pretty surprised. I would have been surprised to figure out who produces the most petroleum in this world. So we'll talk about that in just a minute. But here it is in the United States. These are drilling rig data, and you can see that in the 80s there was a huge spike in the energy costs, and that inspired a whole bunch of people to get involved in drilling for oil, and we had a huge increase in the amount of drilling. So this is drilling, not pumping. This is drilling to find new oil, not pumping existing oil. So it had this huge spike, and then it fell way down. So a lot of these ones that were built, this yellow line is the ones that are in operation, and these ones are the new kinds of ones that are being built, and you can see that in fits and starts it's been declining, more or less declining that whole time. Then more recently, in the 2000s, it increased. We had a big drop in the recession in 2007 and 8. There was a big drop in oil prices, and also just a lot of drop in demand for oil. And but then we've been recovering from that recession. And then in the United States, these are U.S. statistics. In the United States, we've been still drilling and trying to discover oil until very recently. And because of the oil price drop that happened 2 years ago, the amount of drilling for new oil has also dropped. So you might think, if you just look at this part of it, for example, if we're drilling a lot fewer wells, we're producing less oil. That's actually probably true, but it hasn't shown up in the statistics yet. So if you look at here's the chance for these poll things. So actually you did this for your homework. Let's just save the time because I want to get through this. So you all should know the answer to this question. So among these 3 countries, I don't get through it yet. Among those countries, who produces the most petroleum? U.S., right? Was that a surprise to all of you? U.S. outproduces Saudi Arabia in terms of the amount of troops. Now, consumes Saudi Arabia by a large margin, but we outproduce Saudi Arabia. The U.S. is the single largest producer, has been for a couple of years now, the single largest producer of oil in the world. And that's almost entirely due to fracking. So we'll look at that in just a minute. So if it were traditional petroleum that we were producing, that wouldn't be true. And if we were to look at the cost of production, we don't compete very well at all. So in Saudi Arabia, nobody publishes in any very well-confirmed way how much it costs to produce oil. Because just the way they use their oil industry over there, costs of production is just not an important factor for them. So, but the estimates are that it costs maybe $2 to $5 a barrel to produce oil in Saudi Arabia. Costs probably closer to $30 to $40 a barrel to produce oil in the United States. So when we were selling oil for $120 a barrel, we were producing it at $2 or $5 a barrel. Now you can understand why there are lots of Saudi princes flying around in gold-plated jets, and there's a huge amount of money there. So the statistics look like this. So this is the U.S. So again, historically, we were way back well, if you go way back, then the U.S. had produced more oil than a lot of people. But then here is where fracking really started taking off. You can see the effect of fracking on oil production. And then this is the fact that, so here we were both drilling, we were increasing the number of wells because people were drilling all over the place and increasing production. And then we stopped drilling, and production has remained about constant for a couple of years, but new drilling operations have curtailed significantly. And most people think these statistics are always a few months behind. I think the anticipation is that little dip that you see right there is probably the beginning of a larger drop. That there are a lot of these wells that are just not going to be able to remain profitable with current oil prices. That's why oil prices have such a big impact right now on the stock market activities, because current worldwide cost of oil is very close to, it's only slightly above the cost of production in the United States. So a drop in the world, even a small drop in the worldwide price of oil turns a lot of operations into non-profitable operations. And you can see the other major producers here as well. So now, talking about oil, so let's look at the type of oil we're talking about. So this is what's called other crude oil here. It used to be almost everything that we would produce. So when you normally think, this is everything that Saudi Arabia produces, for example. So when you think of the things that, when you think of oil production, drilling and producing petroleum out of the ground, like traditional thought of how you produce oil, that used to be how we produced almost all the oil, not that long ago. So we'll go through, so some of the other things that are on here, the biofuels are, that's mostly ethanol, and this is mostly growing corn and turning it into ethanol and putting that in your fuel tank. So most gasoline contains at least 10% ethanol, especially in the wintertime. It's required in the wintertime to put that much. So what they're really trying to do is oxygen into your gasoline, because that helps to prevent some of the pollutants that would otherwise be there. And then the natural gas plant liquids. So when you produce natural gas, there are some natural gas wells that produce just dry natural gas. But there are many of them that produce mostly natural gas, 80 to 90% natural gas, but a little bit of what they call natural gas condensates. So that's mostly things that are propane or butane or heavier, and they make up a little bit of the natural gas. And it turns out that even now, and especially when petroleum was $100 a barrel, that butane is much more valuable if you sell it to a refinery and they put it into gasoline than if you leave it in natural gas when you burn it in the natural gas stream. So natural gas producers will condense anything that they can condense out of their stream and sell that condensate as a natural gas plant liquid, and that becomes the, for most natural gas producers until natural gas prices are very low again. But because oil prices dropped, the profit margin dropped. For a long time, all the money was being made on that 4 or 5% of what you were producing that you could sell to the refinery, and 95% of what you were producing was at best breaking even in terms of economics of the operation. And then the tight oil. So you can see tight oil is the oil that we get from fracking. And this is oil that has always been in the ground. People have always known it was in the ground, but we didn't have a technology that could meaningfully or effectively recover the oil. So, and then people developed fracking. We'll talk in more detail exactly what's involved in fracking. But because of fracking, instead of producing maybe anywhere from 15 to at most 25% of a reservoir of oil, we can now produce maybe 60 to 70% of that reservoir of oil. And so the amount of oil you can extract has increased dramatically, and there is a lot of oil that just wasn't recoverable at all that is now recoverable because of these fracking techniques. And that in general is called tight oil. That was, the word tight comes from the idea that previously it was too tightly bound in the reservoir to be able to get it out, and now that people have developed this fracking technology will come out. Which brings us to the proved U.S. reserves. We'll talk about these definitions in a minute, but this is just a measure of how much oil there is in the United States. And so it might be a little counterintuitive to think, you would think that as we produce oil, there would be less and less oil available. Eventually that would go to zero. A lot of people, even very recently, were very worried about when that was going to go to zero. And, but it turns out, because of fracking, the more oil we produce, the more we have. All right, so a little counterintuitive. So, because we have developed technologies that make things that previously were unrecoverable now recoverable with current technology and under current economic conditions, then we actually every year we have more and more oil in terms of what we call proved reserves in the United States because of this technology.
So does proved reserves refer only to the oil we can actually extract?
Yeah, we'll go over those definitions in detail in just a minute. All right. In fact, that's the next thing I'm going to talk about. So there's total reserves would be all of the hydrocarbon in the ground, but the great majority of that hydrocarbon, until recently, well over half of it was never going to be able to get out of the ground again. So the total reserves wasn't very meaningful, not very useful to know. So this is true in, for example, in eastern Utah and western Colorado, southern Wyoming, in that region right there, there are lots of oil shale deposits. And there's more hydrocarbon in the oil shale than there is estimated to be in all of Saudi Arabia's oil reserves. None of it, even now, none of it is recoverable. Nobody has come up with a process that can turn that hydrocarbon, get the hydrocarbon out of the geological formation into a useful form that you can use for petroleum. So that's a huge reserve that's pretty much meaningless because it's not recoverable. So that would be part of the unproved reserves, and some of it possibly under some conditions could be recoverable, and some of it probably could be recoverable, and they divide it up that way. This whole part of the discussion doesn't get into the discussion anymore very often because none of this is economically meaningful right now. So the part of this that's meaningful is we start with approved reserves, and we'll go through the official definition in just a minute. So proved reserves, though, is the material we can actually recover, and it makes sense to recover economically and technologically. And some of that's developed, some of it's undeveloped. So people, especially right now, you don't make a lot of money producing oil right now. So if someone discovers a new oil reservoir, they may or may not decide to develop it. They might say, well, let's just sit on it, and in 10 years, prices are going to be way different. We'll produce it, we will develop it then, and we can make a lot more profit. But most of them are developed, and until recently, just about everybody would develop them very rapidly as they find them. And then among the developed ones, there are non-producing and producing deposits. The non-producing ones are mostly ones that people have retired that produced everything they can out of it. So going through some definitions, the reserved are the total quantities of petroleum that could be commercially recovered from known accumulations from a given date forward. The people talk about almost all the time. Proved reserves are those petroleum or gas that by analysis of the data that you have, and with reasonable certainty, this means over 90%, they can be commercially recovered from a given date forward, typically that's now, using operating methods and under the economic conditions and under the regulations that we currently have. So that's a lot of words to just say, this is the material that we can actually recover and sell and make a profit. So, and so the proved reserves are the real, and then the unproved reserves are things that you guess probably exist. So there's like Siberia and Canada and large parts of Alaska even now. There just hasn't been much exploration over most of that area because it's there's just not a lot of economic activity in those areas. So people can say, well, based on what we've done in Texas, we could guess that we would find this much oil in this similar geographic region, but we've never really tried to look for it. So people are just guessing that it's there, and that's part of what the unproved reserves is. So probable reserves are those that with unproved reserves, which might develop. Possible reserves are less likely, so greater than 10%, but typically less than 50% likely to be developed. And then there's developed and producing reserves. Those are pretty self-explanatory. In terms of undeveloped reserves, so undeveloped reserves could be recovered from new wells or undrilled acreage, or from deepening existing wells, or where you can do something to do a new well completion or change the operation in order to recover those undeveloped reserves. Technically recoverable reserves are things that we could actually recover given the technology we have, but either the government regulations or the economics doesn't make any sense for us to do that right now. So they could be recovered, but they probably won't be. So there's, in terms of production techniques, again, this is just have like 2 more slides in terminology. So there's conventional techniques. This is traditional petroleum. That's about 1/3, as you saw from that other graph, that's about 1/3 of our current reserve. So that's the petroleum everybody thinks about when you drill down, poke a hole in, and pump oil out of some resource. Unconventional reserves involve other technologies, and that's about 2/3 of our reserves right now. That includes all the fracking, tight oil material, and the reserves that we get from natural gas. So shale contains oil that can be pumped using unconventional but now common technologies, and this is really unfortunate, but some people refer to this as shale oil, but it's better to call that, so drilling into a shale deposit and fracking it and producing natural gas and oil. Some people call that shale oil, but there's another thing that's called shale oil that is very different than that, and so that's what we usually call tight oil, is the material that we're pulling out of these shale deposits. And that turns out to be very high quality oil. It's very light. It's some of the best oil we produce. So oil shale is a rock. This is what we have in eastern Utah, and the oil in oil shale is so thick, the hydrocarbon, that you just can't get it to flow. Well, a combination of it being so thick and so viscous that it won't flow, and the rock being so, the porosity, or more specifically the permeability of the rock, is so low that you just can't get it out. So the only way that people have come up with trying to produce all of that oil is you actually mine the rock, bring the rock and everything out, and put that in a big oven called a retort, and you heat it up to the point that the oil is now, you break it up so that you can get it out, and the oil becomes more fluid because of the temperature, and then turns out the rocks swell when you do that, so the hole that you made when you mined it is not big enough to fit all of the stuff back in it again, but you go put the rocks someplace else and take the oil out and produce that. So there are a lot of people who spend a lot of money trying to figure out how to make that profitable. And a lot of them are mom and pop organizations, but some of them are more capable organizations, like Exxon, for example. Exxon put $2 billion in the 1980s into trying to produce these reserves. They built a big facility in Colorado, and they were going to turn this huge reserve into something that made sense. And they wrote that all off. So it was a $2 billion expense, which I was in the 80s, so that would be like a $4 or $5 billion write-off right now. And then they laid off 2/3 of their research department because they decided they probably would have never gotten started if they had listened to, if they hadn't, they think they listened too much to their own in-house research people, and if they had more people involved that weren't necessarily part of the company, they might never have made that very expensive decision.
So the rock that's here in the west is all this oil shale rock. So we could, like using fracking technology, you could get into the rock, but it's just too viscous
Right.
to get out. That's kind of
So just getting into the rock doesn't help. So tight oil and gas, which is also sometimes known as shale oil, is unfortunate that there's lots of things you can call it. So this is petroleum or gas that's contained in a formation of low permeability. You go into a shale and you can produce it by rubblizing the shale. You can produce this material now, and that's what fracking has really opened up. So those are some of the big pictures. So now we'll start with where does oil come from and how do we produce it. So any questions first? All right. All right. So first thing to know is that there is the Sinclair plants have a little dinosaur on them. Right? So there's a myth out there that oil is dinosaurs. In fact, there used to be advertisements that would say we're all out of dinosaurs, and that means we're going to run out of oil pretty soon. So the dinosaur content of oil is very, very low. All right? There's not too much dinosaurs in oil. So where the oil came from is, so you start about 300 million years ago. There were lots of plants that grew everywhere. And that's before dinosaurs, and there's all kinds of these giant plants, and animals, including algae and small cellular things that grew in the water, and a little bit of water life. So there actually is, I came up with a way of calculating the dinosaur content of oil a while ago, and you can actually do it because dinosaurs are huge animals, right? But they still have blood in them, but they're so big that they're mostly cold-blooded, not entirely cold-blooded, but they're so large that in order to get oxygen into their blood, hemoglobin, and specifically iron hemoglobin, doesn't work very well. But they have another compound in their blood where vanadium played a similar role as iron does in our blood. It turns out when you burn oil, one of the things that happens is a very small but still measurable content of vanadium in the oil. And so if you calculate how much vanadium there is in a dinosaur, and how much, vanadium is not a very common element anywhere, so if you say how much enrichment in vanadium is there in oil compared to what it would be if there weren't any dinosaurs, you can come up with a way of calculating the dinosaur content of oil. So the dinosaur content is very so the next thing that happened is, so you grow all these plants, and either on land, but mostly in water. What would happen is that the plants would die, and the animals would die, they would collect. And one thing that is not appreciated by most people is, so they collect on the ground, and water comes over and buries them, and then dirt comes over, and over time they get buried under the ground. And so this was coal. So for petroleum, it's mostly these little tiny animals, similar kind of a process, but it becomes an oil or gas deposit. But let's talk about a few of the intermediate steps here. So first you have to generate what the geologists call the source rock. So you need some sort of rock that has hydrocarbon in it. And the way that that's done is by things that are growing in either the water or on land. They die and they get buried, and over geologic time they sink down into the ground. Under high pressure and high temperature, as they get closer and closer, get deeper and deeper in the ground, the temperature increases. They will slowly convert to something that's more mobile. So none of this material is very mobile, but then as it heats up, it starts to move underground. So you start with a source rock, and it migrates out of this source rock, and what most people don't appreciate is that the great majority of it migrates all the way to the surface. Most of that material, including probably over 90%, or maybe even over 95% of the natural gas, and probably 80% of the oil eventually would find its way. It's lighter than the rocks that are around it, so once it gets mobile, it tends to move up and eventually come out of the surface. And that's what you see if you go to the tar pits in Los Angeles, for example, the graded tar pits or places like that. That oil is just naturally coming up out of the ground. It's not an old oil spill that people are dealing with. There's a large fraction of the Gulf of Mexico that has oil that's just naturally coming up out of it. So when they had the big oil spill down there, that was a major disaster from an environmental standpoint, but it was hardly the first hydrocarbon that was coming up in the Gulf of Mexico. There's a lot of hydrocarbons that are constantly coming up from natural sources into the Gulf of Mexico. So most of that material, as it moves around, it eventually will find its way to the surface. When it gets to the surface, so in the long history of the planet, there were plants that didn't need sunlight and ecosystems that didn't need oxygen for a long time. And it turns out we didn't have oxygen in our atmosphere for a long time. And it wasn't only when photosynthesis came into being and photosynthesis started generating oxygen, and the oxygen accumulated in the atmosphere. But all of this stuff, if it gets up to the surface or in the atmosphere, will oxidize and just become CO2 and water again. But some of it finds a different place. So as this migrates around, you can think of some source rock down here, and the oil is coming up, and sometimes there will be what they call, in this case, an anticline or some other kind of trap that has almost no permeability. So this oil is just kind of migrating up through the soil, and it comes to this layer of clay, and the clay is too impermeable for the oil to flow through. And if you have a layer that looks like this, and we'll look at several other formations that will trap clay, but this is a classic, they call this one an anticline. This will come up here and get stuck, and it doesn't have anywhere to go, so it can't go through, and it gets trapped in here, typically with some gas on top of it, and frequently with water below it, and it just gets stuck in the rock formation. So this isn't a big swimming pool here. These are rocks, but these are permeable rocks that the oil can flow through. These are impermeable rocks that the oil can't flow through. And when it gets to those impermeable rocks, the oil just gets stuck. And a relatively small fraction of all the hydrocarbons that were generated and got stuck in these kinds of locations are the sources of petroleum that we're producing right now. The great majority of all that material that died is back in the atmosphere. So we talked about a couple of these things already. So this is the history of the Earth. So humans are thinner than that black line that you see in the long history of the Earth. But photosynthesis started about here. But first life started here, and photosynthesis came in quite a bit later. And there were lots of simple forms of life that were dying. Most of the oil comes from about this region, multicellular life, and more recently, and then very recently, complex life forms developed. You see the dinosaurs, first of all, you gotta appreciate the dinosaurs. So all of human existence is that little bump on that black line that you see right there. Well, look how long the dinosaurs were around, right? So dinosaurs were here for a long time compared to how long humans have been around. We're newcomers to this, so we've had quite an impact on the world. So, all right, so oil and natural gas are lighter than rock, comes to the surface. That's still happening. So we're still generating these deposits, but we're generating them at rates that are minuscule compared to the rates that we're consuming. So materials still are accumulating. The best examples, if you go to peat bogs or oil shale, that's material that's kind of partway through this process. And if it gets buried and stays long enough underground, long enough meaning tens to hundreds of millions of years, that would eventually turn into oil. And so those things are still going on. And it turns out, as much as almost everything I've told you is widely but not universally accepted. There are people who actually believe that oil doesn't come from organic material at all. It's the inorganic material that gets really deep in the ground. Carbonates, for example, rocks. If you get deep enough in the ground under high enough pressure and high enough temperature, they think you can convert that into a hydrocarbon demonstrate that that's not the case for coal. But since oil is a liquid, it's lost to all coal. You can actually see the structure of the plants that it was made from still in the coal deposit. But oil deposits are liquid, and they move through large distances, and so you really can't trace back where they came from with any great confidence. All right, so in the total world oil reserves, conventional oil makes up for roughly a third. There's really heavy oils. This is like in Venezuela that are they're difficult to produce. They're heavier than usual. Some of them are heavier than water. Then there's extra heavy oils, which are even more. These are the tars that people produce mostly in Canada, and then the oil sands and bitumen that you can see up here. So in terms of the total reserves, conventional oil makes up a relatively small part of it. So this is another concept that might be surprising to you. So we think of big oil, right? Maybe many of you are hoping to get jobs with a big oil company. But it turns out that what we call big oil really should be called tiny oil, right? So the Exxons, Chevrons, Shells of the world are minuscule in comparison to the really big oil operations, which are the national oil companies like Aramco and places like that. So big oil is so the size of Exxon, these companies that we call big oil. Oh, this shows you how big they are. So Saudi Aramco is this big, and this is Exxon, for example. So, and British Petroleum, you can see here, Shell there. This is the Chinese national oil production. So you can see that these national oil companies, this is the Iranian oil company, this is Venezuela, these are other national oil companies, NOCs, that are major producers. So they make up these nationalized oil companies are the gorillas in the oil industry. And Exxon and others are, I don't mean to say they're small companies, they're of course huge companies with huge capabilities, but they're small compared to the people they're competing with at Aramco. Actually, in many cases, they're operating the facilities for those companies. And then another thing is that so this shows the oil reserves in several of the OPEC countries as a function of time, and you can see that this was what people estimated as the oil reserve. They publish what they think their oil reserves are, and bang, what happened in 1990 that made this go from here to there. And it turns out nothing happened on the ground. So this is for all of these. So OPEC, everybody knows who OPEC is the oil producing economic cartel. So it's a organization that gets together and tries to set the world oil prices. If they were organized in the United States, they would be put in prison for racketeering, but they're not. All right, so they're outside the United States. So it's the kind of organization that we have laws against to try to control prices in the market. And so they get together and say, we think the oil price should be this, and they set the oil price, and they control a significant fraction of the market, so they can do that. And then they say, and in order to get the oil price to be this is how much oil we should produce, and then they parcel out your production quota, and that depends upon your oil reserves. So if you're a member of OPEC, and you have 10% of the total reserves in OPEC, you get a quota of 10% of the amount of oil that OPEC says you should produce. And so in the 80s, we went through this huge increase in the cost of oil, and at the end of the 80s, the price came crashing back down. Came crashing back down because turns out that you should never trust a smiling oil baron, right? Even in the Middle East. So everybody agrees to these quotas, and then everybody goes home and violates them. So and everybody produces more oil, trying to make more money than what the agreement was. And then they all get together again, and they say, hey, we need to rein this in, and that's kind of what OPEC spends its life doing, is trying to get people to get to OPEC. So if I'm a Saudi prince, for example, and oil prices have just fallen by a factor of 2, and that means that the income for the royal family has fallen by a factor of 2, what can I do about that? Well, one thing I can do is to increase my reserves. And so just arbitrarily, if I say, well, I don't really have 170 million barrels of oil, billion barrels of oil, I have 260. So now I get a bigger fraction of the quota from OPEC, right? And I can produce more oil and sell more oil. So most of these are believed to be that kind of arbitrary change in reserve. And what is important is that this makes it really difficult to know how much oil there really is in the world. Because these numbers, you can't go over in Saudi Arabia, that is, I can't go over there and drill a bunch of things and try to estimate what the oil reserve is. Those are very tightly held secrets. In fact, some people in China have been arrested, Americans in China, who were taking much less sensitive information than this, but just that kind of information, geologic information. There were researchers over there just doing research things, and they got pulled off the airplane, and they're still in China in prison because they were trying to steal these state secrets that China has. So it's really hard to know exactly how much oil there is in the world. In the U.S., you actually have to declare these things to the U.S. Geologic Survey and to the Energy Information Agency. So for a long time, people were worried about what they call peak oil. And this started off from a fellow named Hubbard, who said we're going to produce oil, we're eventually going to run out. And when we run out, think of the chaos that's going to create in the world. Because the whole world has become dependent on petroleum. It's our biggest form of fossil fuel. And so you come up with these curves to try to predict what the production, and that is the U.S. production. And Hubbard said, this is what production is going to do, and this downside is going to be caused not by a change in demand, but by a change in availability of oil. And the peak here was going to be peak oil. So when this was first done, peak oil was going to happen in 1970. And people in 1980, we had this big oil run up in oil prices. And just about everybody was pretty sure we were running out of oil, and that's why the prices were going up. People were panicking everywhere. We created a huge petroleum reserve in the United States to pump enough oil and to store in the United States to keep our war machine operating if we had to keep it operating. But this shows you what happens. These are a bunch of different types of estimates of peak oil at different times, and you can see that more recently they've been produced at, peak oil was going to be in 2000, maybe in 2020, and if you go down and look at other people that have tried to predict this, it keeps getting pushed way out further. And now you can see that the reserves are actually increasing, not decreasing. So it's a really difficult thing to try to predict when we're going to run out of oil. It would be really easy right now to say, because of fracking, we have a huge amount of reserve, and we're not sure what's going to, we have plenty of oil, but there's two important considerations. One is that it is a finite reserve, and among all of the fuels, there's less oil than anything else. So we have a lot more natural gas and far more coal even still than we have oil. So among all the major energy supplies that we have, petroleum is the most limited, even now, even with all the discovery of fracking. And then if you look at the total production, so this is the OPEC petroleum. If you ramp this all the way back to the 80s, they were a bigger fraction, but they're becoming a smaller and smaller fraction of the total oil production. And so here's some kind of oil future summaries. First of all, that the consensus view, even as recently as 2011, was that oil production would become seriously resource constrained in 20 to 40 years. In fact, I'm on a committee, ASME Energy Committee, and we published a paper in about 2007 that estimated that we would have 30 to 35 years of easily recoverable oil, and things would get serious. So that paper is an embarrassment, right? So nobody believes that right now. But even as recently as 2011, people were saying, we've got, in this generation, we're going to run out of oil reserves. They're going to become seriously concerned. So, but another consideration is, and one of the quotes I really like is, people said, the Stone Age did not end because of a lack of stones, right? And maybe that the fossil energy age is not going to end because of a lack of fossil energy. It's going to end possibly because of climate change considerations and other environmental concerns. And what we can say already is that oil resources now, and there's no reason to think this is going to change in the future, are causing huge instability, wars, all kinds of contention all over the world, and that's a problem. That's another reason that people are going to want to get away from these reserves. reserves that cause these kind of problems, and find some other way of transportation and energy in general that doesn't cause that. All right, so what is petroleum? Tell you what, let's take a 3-minute break. Get up and stretch around, and then we'll start talking about what petroleum is, how it's operated. Then what is Exxon going to do? And so the kind of forward-looking research kind of components of that, for the most part, require advanced degrees, specifically PhDs. So, and this might surprise you. It turns out that in proportion to the total number of PhDs, they are overrepresented among management. So it turns out that your likelihood, if you want to become a manager, your likelihood of becoming a manager, at least statistically, is higher with an advanced degree than it is with a bachelor's degree. But there are far, far more people with bachelor's degrees than there are with PhDs, and so most managers have bachelor's degrees. But the proportion of people that are high levels of management anyway are a little higher among PhDs than the bachelor's degrees. So, and there are a couple of other things where an advanced degree would make a difference. So I actually have a whole presentation if you're interested sometime about this. The bottom line is this. You make slightly, so you make more money with a PhD, well, let me talk about a master's degree first. So in most cases, people with master's degrees do the same jobs just about as people with bachelor's degrees. You frequently will have, if you have a master's degree, you might be put in charge of design as opposed to operation a little bit. People expect that you're going to be a little more confident with the science part of things, but master's and bachelor's degrees usually qualify people for about the same jobs. PhDs are a whole different world. If you get a PhD, you're making a statement about what you're interested in doing, which is not operating a refinery probably, and not even designing distillation columns that would go in a refinery, but you're interested in doing research and working in a research shop or doing something forward. Now, let me talk a little bit about research in industry. So this is an exaggeration, but it's pretty, there's a lot of truth in it. So one of my industrial friends told me the other day, so we're involved in a company that's we're building things that have never been built before, designing things that have never been designed before, trying to do things that nobody's done before. So to me, this is, so we think we're doing commercialization, but there's a lot of research involved in this commercialization. But I'm talking to somebody from a more traditional company and showing him what we're doing, and he says, let me explain what research is like in our company. It's a very large energy company. He said, research for us means that we go find a piece of equipment that's doing exactly what we want it to do, under the same conditions, processing the same material, it just happens to be in a different industry. And then we try to decide if we unbolt that piece of equipment from this industry and bring it over in ours and put it into our industry, will it still do the same thing? And so research now that's not fair to some very, very capable and forward-looking research people in industry. In fact, some of the most productive research organizations have been tied to industry. Bell Labs, which doesn't exist anymore, but Bell Labs was probably one of the most premier research institutions we had in the country for a long time. There's an Imogen research facility that IBM runs in San Jose, which is world-class. So they do better research there than happens at universities or national labs almost anywhere. So there certainly are fantastic research institutions among industry, but it's traditional, industrial, not. So both of those are kinds of institutions that have been built just for research. But if you're in the mainstream company doing research in the mainstream company, it's not going to be quite the same as university research or national lab level research. So I saw some hints.
Oh, well, I was wondering if you thought they would change that trend of bachelor degrees and how they would,
All the renewable energy stuff.
well, I was wondering if there would be more of a trend of more
PhDs
masters
in the
and
future.
PhDs and how they would,
I don't think the fraction of people who get PhDs has changed appreciably in the last little while, but I might be wrong. I haven't looked that up. That's an interesting question. But don't see that changing. So if you want to do kind of operations and traditional design, I don't think people are going to be hiring PhDs to do that. I don't see any reason. So I hate to admit it, but the reality is once you leave school, you are going to be vastly overeducated for almost all of the jobs that you take in most of these companies. So you will wish that you so running what the engineers do, it's the technicians that have all the fun. So what the engineers do is you might be in charge of a bunch of tanks, for example, and it's important that you have an engineering background so you know what's going on in these tanks. But really what your job ends up being is ordering stuff, watching how full the tank is and ordering more fluids or whatever it has to go into that tank to make sure that you always have the material that might be used to operate for it. You're going to have a big distillation column and it's been there for 50 years. And you already have a model that's way more sophisticated than it needs to be to describe that distillation column. And you're just in charge of making sure that nothing goes wrong with that. And if something does go wrong, if you have to replace a pump, you don't even get to do that, all right? So you work with a bunch of technicians and you tell the technicians, we need this pump. And you call the vendor, and the vendor will help you decide what pump you really need. And then you and the vendor decide what pump you need, the pump comes in, and the technicians are the ones that get to tear everything apart, put the new pump in, put all that together. And so why would you go to graduate school? So one thing is, so you make more money, your initial job offer with a PhD, for example, is more money than you're going to get with a bachelor's degree. But you've also spent a bunch of years making, actually, I think, a reasonable amount of money. At BYU, we pay our graduate students. So ChEn is one of our graduate students in the back. So he doesn't look like he's being too bad there, Jews, right? So we pay our graduate students typically $20,000 to $23,000 or $4,000 a year. That's what this gets into your pocket to go to graduate school, which is enough to live on. Not buying houses and cars and stuff like that, but it's a small fraction of what you make if you go to get a degree. But you've spent maybe 4 years making $20,000 a year-ish instead of making $70,000 or $80,000 a year that you might have made in the oil industry, and it takes a long time to catch up to that, even though your salary's higher. But if you do the analysis, it makes about, by my calculation, a 10 to 12% difference in your lifetime income. If you get a graduate degree, so you make a little bit more money. But the reality is you're all going to make way more money than you need. If your problem is money, if you're working in any engineering field, it's not the amount of money you're making, it's your ability to manage the money that you're making that's the problem. So the real reason to get an advanced degree, I think, is not for the money, it's really for what you want to do. So, when we have more time, we got to get to the point where you can do homework here, so I'll finish the rest of this. Somebody remind me sometime to talk about masters and patrons and why you really should get an advanced degree. All right, so oil, this is crude oil composition. So oil has this composition, it's mostly carbon, as you might guess, on a mass basis. On a molar basis, it's mostly hydrogen, but on a mass basis, it's mostly carbon. And but there's a lot of other things in it, a little bit of nitrogen, a little bit of oxygen, a little bit of sulfur. Both nitrogen and sulfur are essential for plants to grow, nitrogen in particular. So there's a little bit of nitrogen from the plants, but in the case of oil, most of that gets filtered out, and then there's a little bit of inorganic material. That's where the vanadium comes in. It's a very small amount, but you have a little bit of that in there. So in terms of its molecular, that's its elemental composition, its molecular composition. So it's mostly naphthalene. These are, so a little bit of paraffins. So paraffins, you remember what paraffins are? Candle wax is paraffin, right? So they're aliphatic hydrocarbons. Naphthenes are cyclic but non-aromatic alkanes. So these are like cyclohexane, those kinds of things. Some aromatic mixed material in there, like benzene, and some asphaltics. These are large aromatic clusters where you have several aromatic rings together clustered into a big molecule that is really heavy. So we classify oil this way. It can be light, intermediate, heavy, or very heavy, and that depends upon the density, which is an American Petroleum Institute, or goes by API standard. And we call that gravity. And it can be, so first of all, gravity is measured in degrees. All right, so light means that the gravity is greater than 31 degrees. And turns out that higher the gravity, so the larger the gravity number, the less dense it is, all right? So it's easy to get confused here. So if it's above 31.1 degrees, that's the most valuable oil, and that's the light oil. And that's what everybody would like. Intermediate oil is between 22 and 31 degrees, and heavy oil is 10 to 22 degrees, and very heavy oil is less than 10 degrees. So very heavy oil is the only one that's more dense than water. So very heavy oil will actually sink in water. The rest of them float on top of water, but they're light. Now look at the formula for how you calculate API gravity. So it's 141.5 divided by the specific gravity minus 131.5. So this term, which is never going to change, it's well established in the oil industry, but it's just on almost every front it's asking to be misinterpreted. So the gravity, as gravity gets bigger, the density is getting smaller, right? So as the gravity is measured in degrees, not in normal units that we would have. So why we don't just use specific gravity is a question, that history has answered for us. But when you talk about it, these are the classifications. So it can also be classified as either sweet or sour. So sour crude contains sulfur, specifically more than 0.5% sulfur. Sweet crude contains less than 0.5% sulfur.
Is that weight?
That's weight percent. So everything, almost everything in the energy industry is done in weight percent, because it's, how do you define a mole of petroleum, right? It's got a bazillion different kinds of actual chemicals in it. So everything's done on a weight basis, and almost everything. This, by the way, is terminology that would be good for you all to know. So the sweet-sour terminology gets used not just for oil, but for lots of things. You'll talk, so frequently people talk about sour gases, which means gases that contain either sulfur dioxide or nitrogen oxides, or sometimes carbon dioxide, or sour gases, acidic gases, as they call them, the forms of solids. So if you look at the quality of oil around the world, so this is the sweet-sour scale, and this is the heavy-light scale, and you can kind of see where different places fall in the world in terms of average. So this is the definition. This West Texas Intermediate is a benchmark oil that you're referred to all the time. We actually don't produce very much of this, but it's a standard, which is a benchmark standard that says if you had oil of this quality, this is how much it would sell for on an international market. Another one you hear a lot now these days is the Brent crude, which is a similar standard, but it's based on oil that's produced in Europe, mostly out of the North Sea. So those are the two most commonly cited oil prices that you'll find. And so if your oil is heavier or more sour than West Texas Intermediate, it will sell for a little bit less. If it's lighter or less sour, it will sell for a little bit more. But this is just the benchmark standard. Not all oil sales sells for the same price, but that's the benchmark that people follow. In fact, that's what we talked about here. So West Texas Intermediate and the Brent blend are by far the most common standards that we cite, but there's internal to the Middle East, there's a Dubai oil standard. Malaysia, you can see there's a bunch of other standards that people talk about, but far less frequently than those two. So if you look on a diagram like this is a case where we can look at, this is elemental composition. So if you take the ratio of oxygen to carbon and the ratio of hydrogen to carbon, coal, heat, biomass, energetic materials means things like rocket motors and explosives. Diesel oil, gasoline, and natural gas all fall in a diagram that looks about like this. Black liquor we'll talk about. Probably I've never heard of that. But you can see that they kind of fall on this diagram in different places, and that's useful for classifying both the fuels and how they operate. So these are just cartoons, but these are actual measurements from samples that I've had in my laboratory, a bunch of different fuels. Biomass is the green, black liquor is black, coal is over here. I didn't put the oils So I'm not going to spend too much time on these jobs because we need to get to your homework, and nervous if we're going to make it all later. So talked a little bit about, so these are the things, reservoir data that depend on. So first we'll talk about the geometry of the trap. So there are several different ways you can trap oil. We talked about the anticline earlier, where you have just a swell of a rock that for whatever reason, these layers that initially are laid down always horizontally, then over time, because of the way that things shift around, if you get an anticline form like this, then that will trap oil. Probably more frequently now are stratigraphic traps, where you have, instead of an anticline like that, you have some sort of formation where you're going to trap the oil because you have an permeable layer here, and a sand layer, and another layer that the oil can't get through, but the sand layer disappears and this gets caught in the wedge there and it disappears. Or even more frequently, and this is part of the great challenge with oil wells, is if you have a fault, then this breaks, a fault line will shift these layers like this and will frequently create a trap where oil will get caught in the fault, which means a lot of oil wells are drilled right on or near faults. And so that makes everything even more complex in terms of how you're going to operate and safety issues and everything else. So that's a pretty common kind of a thing. So how do we find the oil? There are lots of ways to do this. One of the jobs I had when I was still in school, before I graduated as an undergraduate, I spent one summer as a doodle bugger, and this is part of a doodle bugger's job. So in our case, it was a helicopter-based operation, but it's similar to this operation here. Where my job was to drill. So there was a group of people that stayed very clean, and as far as I could tell, shouldn't have been paid for doing anything. They would just walk through the forest and stick these seismic phones everywhere in the forest and little red flag. And then we would come in the filthiest job that I've ever had, but I was young and it was great at the time. Every day we would work more than 12 hours a day, and you'd come back as dirty as you could possibly be every day, just covered in mud and dirt. And our job was to drill about a 100-foot well and put about 100 pounds of dynamite at the bottom of that well and cap it off. And then the next people who should have had to pay for their job came by, and they blew up the dynamite. And what they do is when they blow up the dynamite, that sends these little vibrations down in through the earth. And these seismic phones that the first crew put on the land would measure how the earth shifts. And then you send all that data to a group of, and in this case it probably is PhDs, sitting in Texas, and they would look at all those measurements, and they would try to come up with a map of what's under the ground here, specifically because these waves go through different layers of rock in different ways. They can tell whether there's liquids or solids and how dense the solids and liquids are, and try to detect if there's an oil well. So they're getting better and better at that, but it's still just an educated guess. So it's a very expensive operation, but that's a way that you can make an educated guess of where you might find
Do they
oil.
still do it essentially the same way?
So they do. So frequently they do still have the helicopter. Well, right now not so much because oil prices are so low. But when oil prices are really high, everybody's anxious to find oil. So and so sometimes they'll use trucks to drill the wells. It's way cheaper than the helicopters, but they can't. I was in the top of the Gray Mountains in northwestern Wyoming. If you've ever been there, you can appreciate that no truck would have survived even a mile of that driving up through there. So so trucks can do the same type of thing, or sometimes they'll just do it right on the surface, not drill the well, which saves a lot of money, but the data isn't as good. And sometimes they'll just guess. They'll just look at it and say, well, we're not even going to do any of this. We'll just drill and explore here as well. So the next step after this, if you think that there's oil there, then they'll drill not a production well, but just an exploratory well, relatively narrow well that they can drill rapidly and go down through the ground and sample the rock cores and bring them up and see how much hydrocarbons there. Then if they think they have a reservoir, and there's a lot of jobs here, and a lot of these can be bachelors, but these sometimes are also advanced degrees. So you set up this model of your reservoir. So this is what a reservoir might look like. This is an actual 3D picture of one of the reservoirs that people were trying to produce. So under the ground, you think you have oil in these deposits, And this is what it looks like. This all might be 6,000 feet under the ground, and this might be at most a few hundred feet, sometimes only a few tens of feet thick. And but it's pretty big, and you drill down in there and you say, and this is where things get really dicey. So you might have actual measured data at best in 5 or 6 locations in this. You know, you could take a sample here, 5 or 6 actual measurements. And then your job is to describe this whole thing and how the fluids are going to flow through it as you try to produce it. So, drill down in here and you try to extract the hydrocarbon as best you can. And the way that you do the drilling is, I'll tell you what I'm going to do. These drilling rigs are going to be really fun to talk about, but they're not going to help you get your homework done. So let me go to what you need to know to get your homework done, and then we'll come back to this. So in that reservoir, the description of how things flow through a reservoir is given by Darcy's law, and that says that the volumetric flow rate in the direction x is proportional to the pressure gradient in that direction. So this is the scalar version of this. If you turn that derivative into a gradient, it would be the 3-dimensional version. So if you double the pressure gradient, then things are going to flow twice as fast in that direction. But this proportionality constant involves this K, which is a permeability divided by the viscosity of the fluid. So the more viscous the fluid is, the slower it flows. That makes sense. And permeability is how easy it is to get through the rock. So a measure of how porous and how tortuous the pores are. All of the things that go into describing how fluid moves through rock. Let's see. I can't remember if I didn't say this. I'll emphasize it again. So reservoirs are not big oil-filled swimming pools underground. They are rock, which is saturated with oil in the pores of the rock. Once you produce the oil, well, the rock is still there, so you're just trying to move porous material out of rock, and maybe only a few percent, maybe more, maybe something like 10 or 15% of the total volume is hydrocarbon, the rest of it is rock. And so, so sandstone, for example, has got about a 15% porosity, so it's rock like sandstone, and the oil just flows through. All right, so in your homework, I'm going to have you calculate flow rate. So let me show you, let's see, this is for multi-phase flows. We'll go through that in more detail, but I have an example here of how you do this calculation. So you need 2 things, Darcy's law and the continuity equation. And let me just get to the example, looking at the clock. All right, so we're going to say, in this simplified example, we start with incompressible flow with no gravity, and so this is just the continuity equation. If you go through the traditional thing and ignore all the terms that are too scary, you end up with, for Darcy's law, you end up with this kind of a thing, and in a homogeneous reservoir, you just end up with the second derivative of the pressure is 0. So I actually have this worked out in great detail. Here we go. Okay, so let's say we're doing this in, is this a spherical? Yeah, spherical. So we're going to say we have a spherical, well, all right, spherical oil reservoir. And we're going to try to predict what the flow rate is and how that depends on things. So the first thing you do is you set up the continuity equation, which is here. And that's symmetric with respect to both angles, and so we ignore theta and phi. So almost never have you ever used theta and phi in spherical coordinates, right? So I'm not going to use it here either, so we end up with just this equation. And so that boils down to this. You can solve for C, and you end up with an expression for the pressure that says the pressure is going to equal the pressure at the outside of this sphere that we're going to define as some location minus, so the pressure is going to decrease as R gets smaller and smaller because the negative sign there is decreasing. So the pressure starts off here, and then we have a well in the center of this spherical thing that's sucking oil out of there. And as you get closer and closer to the well, the pressure gets lower and lower. That makes sense, right? All we really need from this continuity equation is an expression for pressure and how pressure depends upon position. And then we put that in Darcy's law. So Darcy's law says the volumetric flow rate is the permeability divided by the viscosity times the gradient in the pressure. So I take the derivative of that pressure equation with respect to R, and substitute that in here, and I come back with the volumetric flow rate, and if I multiply that by the density and the cross-sectional area through which it's flowing, I get the mass flow rate. And this says that the mass flow rate is going to equal, and you see that the mass flow rate doesn't depend on R, which might surprise you a little bit until you think about it. And like most problems, if you think about it for a few minutes, it should be obvious. So if this is a steady state solution, so we're producing this in steady state, then if I'm moving material in steady state and there's only one dimension in this problem, then if I just have a whole bunch of concentric spheres around the point that I'm extracting the oil from, does it seem now obvious to you that I'm going to have the same amount of mass flowing through each one of those spheres as I move inside? That is, I couldn't have a different amount because it would have to be accumulating or depleting something. So the velocity changes because the closer I get to the center, the faster it has to move. So I can calculate the velocity from the volumetric flow rate or the mass flow rate, but the mass flow rate ends up constant. Is everybody good with that? And in most one-dimensional problems, you'll find out that the mass flow rate expressed in some sort of coordinates is always going to be constant. Oh, I guess we could also look at, so the more permeable the rock is, the faster I can produce. The less viscous the oil is, the faster I can produce it. And so see, the greater the pressure difference, the faster I'm going to produce the oil. And in all cases, in this particular case, they're linearly dependent on those parameters. So bigger pressure difference, that is, I'm pumping harder, smaller viscosity, and the material moves through the rock easier, or more porous rock, more permeability, will all lead to higher production. All right, so in your homework, you're going to do the same problem, except in Cartesian coordinates instead of spherical coordinates. So that's actually easier for most people. But you just use the continuity equation, and I think all of those equations are given to you. Use the continuity equation, set up the equation, come up with an expression for how pressure is going to vary in Cartesian coordinates. So what you have in mind, what you should be thinking of is, in this case, I have a pressure here, and a pressure here, and I need to figure out in Cartesian coordinates how the pressure is going to vary from one point to the next. And you should be able to guess in Cartesian coordinates about how that's going to be. All right, so I'll let you figure it out, but it should be fairly evident to you. And once you know how the pressure varies with respect to x, you put that in this equation. So the gradient of the pressure in Cartesian coordinates is just the partial in pressure with respect to x. So you take the derivative of this expression for pressure, put that derivative of the expression for pressure in this equation, and that'll tell you what the volumetric flow rate is, and then you can calculate, if you know what the volumetric flow rate is and the density of the oil, you can calculate the mass flow rate or any other property that you want to know, velocity. Or I think the homework problem asked you to calculate the velocity. So you feel like you're ready for that problem?
You said the continuity equation in Cartesian coordinates is given to us. Is that in the homework or in the notes?
Well, so yeah, it is, but it should be evident to you. So it's in the, I'm almost certain it's in the homework problem, but you should. It's the same equation that you use in fluid mechanics and everything else. So it's a steady state, and if it's incompressible, then it's a pretty simple equation to solve. All right. All right. So we got 5 more minutes. So we'll go back. Did everybody feel like that shouldn't be too difficult? So it's a little bit of math, but and it's the simplest imaginable, simplest description of an oil reservoir that you can get. All right. So let's talk about fluid properties. We talked about the density. So these fluids can be treated as incompressible in almost all cases. This is where you get these kind of data from these kinds of measurements. So I guess this is a good diagram. So to give you an idea of what how permeability varies with different kinds of things. Permeability of, so if you start off with just gravel, the permeability as measured in centimeters squared is about 1/1000 for gravel. So it's pretty easy to move fluids through gravel, right? So that's a really low permeability, or really high, really high permeability, so really low resistance. So these are called pervious rocks. So sand and gravel and fractured rocks, things move through there pretty easily. And then semi-pervious rocks are peat and fine sand, silt, loam, layered clay, and most oil reservoir rocks fit in this semi-pervious layer. So there's not a lot of gravel or just sand that deep in the ground. It would have been compressed in high temperature, would have been compressed into more rigid rocks. So most oil reservoirs are in this semi-pervious layer, so you would expect permeabilities on the order of 10 to the -8 square centimeters. Sandstone is at the bottom end of that, and then if you get into highly solidified rocks like clay, limestone, dolomite, and granite, these are impervious rocks. So they're still not zero, so the permeability isn't zero there. And in fact, if so many of you will soon be buying homes, and you're probably all going to want granite countertops in your homes. And what you'll find out with these granite countertops is if you spill grape juice on them, they're permeable enough that if you don't wipe it up right away, you'll have a grape juice stain for the life of your countertop. And it'll seep into the countertops because of the permeability of the granite. So it turns out that the cheap formica is much more functional than very expensive granite, but people like granite. So granite, about half the granite also emits radon, which is a poison that will give you cancer. But still people like granite, all right? So, so we'll talk about radon a little bit more in the future. All right, so I think we're done. Any questions?
How deep is the average oil well?
So the oil wells vary quite a bit, and over time they've been getting deeper, but a typical oil well is 5,000 to 6,000. Typical producing oil well is 5,000 to 6,000 feet. No, we'll pick this up from here. We haven't